Sure. Yeah.
Okay, so we're going to start with 2.5 axis milling. Um, and the part that we see here, the main thing we added, well, one of the things we added is cutter compensation for hole pocketing and profiling. I did just want to mention that if you have a hole that you need to cut and you need very tight tolerances, um, up to 6 or even higher if you need it, hole pocketing and profiling is the way to go. You can get very tight tolerances, like if you got a press fit or a loose fit, say of a bearing or a sleeve or something. This is the method you want to go to. And now that we've added cutter compensation, it makes it even better if you're cutting production holes or just if you want to use the compensation feature in your controller. But we've added cutter comp for hole pocketing. On the left, you see hole pocketing. On the right, you see hole profiling. And over here in the dialog, it works very exactly the same way as other cutter comp and other 2-axis operations. Um, just turn it on, and when you post, now I do want to make a mention of the post for cutter comp. Cutter comp does have to be set up in your post in order to output the G40, G41, G42, etc. In your G code file. So if you're posting and you're looking for it and you don't see it, um, uh, just contact us or send us your post definition file, and we'll add those criteria to it and send it back to you. Okay, so this is one of the main things in 2.5 axis milling. Let's go to the next one. I think I have another 2.5 axis. Yes, we have enhancements to our thread milling feature. This is actually a rather popular operation type. People wanting to cut threads either in holes, if they just have a tap drill or a single pitch tap drill. You can use either one, and you can cut rather large hole threads, both internal and external threads. But if you look on the left here, you'll see the parameters that we enhanced and added to the thread milling. The start depth is interesting because if you want to leave such like a relief depth before the thread starts threading, you can use the start depth, and the threading will start obviously at the depth that you specify. So it'll start at the start depth, and then it'll go down to the hole depth, the thread depth, sorry. And we also added for thread pitch control. You can now specify threads per millimeter or per inch based on the units of the part that you're working on. And then also a cool one, number of starts. This will ensure that you have a number of full threads. And correct me if I'm wrong on this, Joe. The number, if you have one start, you'll have a thread that goes 360 degrees. It may be broken up into 180 and 180. But if you have this set at 2, you'll have another full thread. Excuse me, another full thread. And if you have it set at 5, obviously you'll have 5 threads. So you have more control, basically, on
Yeah. So
thread.
basically the start angle will determine the first start, and then 360, the full 360 will be divided by the number of starts to give you additional.
The first thing we're going to take a look at is 2-axis enhancements. So we've got a prismatic 2-axis part. It's got a bunch of holes. One of the things that we're going to show you here is the enhancements in both the hole pocketing and in the thread milling. So in this part here, we have an M40 metric thread that goes through the base of this part. And in order to start that operation, or prior to starting that operation, we want to clear out, rough out the material, and get the inside diameter machined of that thread. So we need to do that ahead of time before we can do the thread milling. So let's go and look at hole pocketing here. So the first thing we're going to do is we're going to pocket out the hole and leave some allowance for the thread. So let's take a look at hole pocketing. Okay, so what we're going to do here was we're not going to select the whole perimeter, okay, because that doesn't represent the exact inner diameter of the thread itself. Okay, so we're going to select a point. Okay, we have selected a point right in the center. So we'll go on to the tool. So we're just going to use a flat mill, 12 millimeter diameter flat mill, to hole pocket this out. For the cut parameters on the hole pocketing, the enhancement in version 2025 that we mentioned is compensation. So now you can apply cutter compensation, right or left, on hole pocketing. So we got compensation set to auto on, and we've got other cut parameters set. A few that's of note here is make sure you select the location of your cut geometry. In this case, we have selected a point, okay? And that point lies at the top of the hole. It's not at the top of the part, as you can see, but it's at the top of the hole, and that is at top, okay? So also, we have a hole depth that we just used the measuring tool to go ahead and calculate that depth. And we also have a hole diameter. Here's where I mentioned that we didn't want to use the diameter of the hole as modeled because we want to make sure that we're cutting to the minor diameter of the thread, okay, which will be smaller in diameter than this hole itself. So we calculated that needed to be 39.796 in diameter. So that's the minor diameter of the M30 metric thread that we're going to be thread milling in that hole. Okay, so one thing to note, you want to make sure that you're using a point so you can specify the diameter. If you check this and use arcs for diameter, it'll just cut to the diameter of the hole itself, and that's not what we want. Okay, so what else do we have on here? Everything is pretty straightforward. We're adding a cleanup pass at each Z level just to make sure we get the, as much accuracy we can get out of the hole pocketing. Now the diameter of the hole pocket is not going to be the finished diameter. We're going to come back with a hole profile. So we can go ahead and go ahead and check that. That could be unchecked, but we'll leave it checked. Entry and exit. For typical for hole pocketing, we have a helical entry. So we got one helical entry at each cut level. So it's going to helical down and it's going to do a cleanup pass at each level. Okay, so we have a helix diameter of 1/4 of an inch or 6.35, and then we have a height H of 6.35. Okay, sorting, we're not going to do any sorting, we're only cutting one hole. And then also in 2025 we have feeder optimization parameters. We're not going to use those in this case. Okay, so let's just generate that. So we have a hole pocket. Okay, we got one helical motion, and then we have a cleanup pass at each cut level. If you look at front, okay, you'll see that we have a helical entry and then a cleanup pass. The blue motion is a cleanup pass at each cut level. So there's going to be 3 cut levels. Okay. Okay, so that is the whole pocket. So that's basically a roughing operation for this M40 metric thread, inside diameter thread. So based on that, let's go ahead and simulate that. Since we're at here, let's go ahead and turn the stock off. Now you will find that we haven't done any other roughing off, so you're going to see this hole stick up a little bit higher. Let's go ahead and play that. Okay, so we got the hole pocketing. Let's go ahead and look at the profiling. So in hole profiling, you have one helical motion to the depth, full depth of the hole, and then a cleanup pass at the base of the hole. So this cleanup pass is what really zeroes in the accuracy of this hole. So this hole profiling, let's take a look at that. We're using the same point, the same tool. So in the cut parameters, we have compensation on again, and we have location of cut geometry similar to the pocket at top. Okay, and the hole depth is the same at 19 millimeters. And then also for the hole diameter, we're using 39.796. That is the minor diameter of the hole. And we're going to uncheck use arcs, and everything else looks okay. Entry exit, we got lines and arcs, so we got a 1 millimeter entry, linear entry, and then also linear engagement, a linear retract. Okay, and let's see, that all looks good. No sorting, no optimization. Let's go ahead and generate that. So here is our hole profile, if you look at it here. So this is the minor diameter of the thread. Okay, so keep that in mind. We're not cutting all the way to the hole. Okay, so let's go ahead and show you what that looks like. So if you look at this is the M40 hole here on each side, and this is the helical motion of the hole profiling operation. Then we have a cleanup pass, circular cleanup pass at the bottom. And again, we have cutter compensation enabled. So now what we've got this set up. Let's go up here to isometric view. Okay. Let's change this view. Okay. So now we have the hole prepared and it's ready for thread milling. So let's go into the thread milling operation. So again, we're not going to use the point for the thread milling operation. We're going to use the circular diameter, because we're going to specify the parameters for the thread in the dialog. So this circular diameter is just more of a locator. So we're going to pick the tool, and as you can see, we have a tap tool. Let's take a look at that, or a thread tool. Okay, so we have a thread mill tool, and what's critical here is the 1.5 millimeter pitch. So this is the distance between thread to thread for the M40 metric internal thread diameter on this part. So these other dimensions that not that critical, obviously there's got to be, you know, smaller than 40 millimeters, but you're using a single point tap tool. So this tool will only have one thread on it. Okay, it's not going to be threaded all the way down, so we'll just have one thread. Okay, and the distance from the beginning to the end of that thread is the pitch of 1.5. So that's the major parameters that you need to make sure you got down correctly. The pitch diameter is critical, so that has to be correct. Let's exit out of that. So we have our single thread tap tool specified. So let's look at the cut parameters for thread milling. As I mentioned, the hole itself is just a locator because we're going to specify the diameters here. So we're doing an internal thread. It's going to be an M40 internal thread. We've got compensation on, cutter compensation turned on. It's available in thread milling as well. So we've got a right-hand thread and an internal thread. So the major minor, since we're doing an internal thread, it will be the minor diameter of the thread itself, and that's set to 39.796. Okay, and then a total thread length. This is set to 18 millimeters, but I think that needs to be 19. Set that to 19. The start depth, this means where in this depth you want to start cutting the thread. We want the thread to go all the way through from top to bottom, so the start depth is set to 0. And for the pitch control, we're setting it to a pitch at 1.5 millimeters. So that is critical. That has to match the tap tool that you're using. And 2025, we added some additional parameters. You can specify the pitch by threads per millimeter if you want to use that value. We also added a start depth if you wanted to give some relief to the thread. Okay, and a start angle, leave that set to 0 for the standard metric thread, and the number of starts is 1. That's for a standard metric thread also. So the entry and exit, you'll see that we have a linear entry of 1 millimeter, and then we have a radial engagement edge clearance of 0.6. Okay, we're not going to use any feed rate optimization. Let's go ahead and generate that. Okay, so here is our thread. So here is our M40 metric internal thread with a thread pitch of 1.5. So it's 1.5 between each thread. Okay. So when you, as you can see, you don't actually see the thread, and we don't actually simulate the actual shape of the thread, but the control geometry is there to create the thread. It's one helical motion, a thread diameter, okay, and it's got an entry, and it's got a helical ramp entry to the start of the thread, okay, and it's going and it's cutting at a pitch of 1.5 millimeters from top to bottom. So let's take a look at what this looks like when we post it out. Let's go ahead and look at the post for a moment. Okay, let's see what else we got. We got a couple of posts here. Haas CutCom, let's go ahead and select that. And we'll pick OK. And we're going to do the, when you run this on the machine, obviously, you know, this hole here at the big hole here at the top is all going to be cut out already. So we're just looking at the operations needed to do the hole pocketing and the thread milling. So let's do the hole pocket. Let's go ahead and post that. So what we got here is we got the hole pocket, and we have a G40 which is turning off the cutter comp, and then we got a G41 which turns on the cutter comp for that dimension, and that continues on down for the entire thread, or the entire pocket, excuse me, and it should turn it off at the bottom. Okay, so we got cutter comp in the hole pocketing. Let's go ahead and look at the hole profile. Post that. Okay, very similar. We've got a G40 to turn off cutter compensation at the start, and then we're doing a G41 turning on the cutter comp for the perimeter diameter of this hole. This blue motion here at the bottom, okay, that's the full cleanup pass. That's going to be assigned to the G41, where you can offset it at the controller. Now, just a note about cutter compensation. If you're not familiar with what it does, there are some misconceptions out there that it's only for compensate for your tool wear. Yes, You can compensate for your tool wear, but that's only going to come into play if you're doing production parts. Okay, so if you're running 100 parts an hour, okay, you're obviously going to have a lot of tool wear, and every time you do your dimensional check, say every 100 parts or every 50 parts, you do your dimensional check. You can make those adjustments on the controller using the cutter compensation offsets for each of the tools. That's how it's used. One of the ways it's used in production. But in most cases, our users are not running production. Well, they do in some cases, but a lot of other users don't. Okay, so what would you use cutter compensation for if you're not running production? Well, think of it this way. Any operation that you cut, okay, you're going to have a setup, you're going to have stock, and you're going to have a tool, and you're going to run it. So the very first time you run it, okay, it may not be exactly positioned correctly, depending on the geometry, depending on the cut, what you're doing, okay. You may measure that while it's sitting right on the table, okay, and you may see that it might be a little off in the X or the Y, not because of the program, but just for the variations in how you might have set up the part on the machine, okay, where your work zero is, etc., etc. So what I'm getting at here is you can use the cutter compensation to dial in the accuracy, to make some adjustments at the controller to get this first piece the way you want it. Because your first piece in your particular application is the only piece, okay? So you can use that cutter comp to make some adjustments while the part is on the table, okay? So that's a good thing to remember about cutter comp. Okay, so let's also look at the thread. Let's post the thread out. Okay, so here is our thread. Again, we got G40, which is turning cutter compensation off. And then we have G... And then we have here a G42, turning cutter compensation on, okay? And it should turn it off near at the bottom. Right there, it's turning off cutter comp. Okay, so now, just as a recap, in 2020 version 2025, you can use cutter comp now in hole pocketing and hole profiling. Hole pocketing and hole profiling is the go-to operation if you need to cut a larger hole with exacting tolerances. For example, if you're going to press fit or do a slip fit or a loose fit of a bearing or a bearing sleeve, okay, you can use hole pocketing, specifically hole profiling, to get an exact hole diameter that you need without using a boring bar. And we have a video, and I'll put a link to it in the description, of one of our users using it exactly like that and getting the exact slip fit that he needed, no boring bar, just using hole pocketing and profiling. Okay, so we got that. Let's go on and look at the 3-axis